In this set of notes, we're going to be learning about scientific notation, how to convert from standard notation to scientific notation, how to order numbers in scientific notation, and how to multiply and divide numbers in scientific notation. So first, let's learn what scientific notation is. Standard notation, think about that as just normal. It's a number written using normal place value. So like 1035, I would write it like that, or maybe 0.0035, which is 35 tenths, hundredths, thousandths, 10,000ths. So I can write numbers in normal notation. Scientific notation is useful as a way of writing very, very large or very, very small numbers as a power of 10. So we'll talk about the notation first. It might seem confusing, and then I think once we actually get into practice, it'll make a little bit more sense. So scientific notation is going to be this number called c times 10 to the n power. And there's two parameters on scientific notation. One, the easy one, is that n just has to be an integer. So n can be positive or negative. It just can't be a fraction or a decimal. So like n can be 5 or n could be -7. C has to be between 1 and 10. It can't be as big as 10, and it can equal 1. So the thing about C is it's always going to be a number where it's one digit followed by a decimal, and then however many digits follow that does not matter. So this number on this single spot can be a 1 through 9. So the number could be 1 point anything, 2 point anything, all the way up to 9 point anything. So it could be like, for example, 7.635. The amount of digits after the decimal don't matter. What matters is that there's one digit before the decimal place. The power of 10 is going to tell us where to move the decimal point. So if the power of 10 is positive, so let's say it's like +3, so 10 to the third, we would move that many times, so n times to the right. And if the power of 10 is negative, we're going to move that many times to the left. And that's how we're going to convert from scientific notation back to standard notation. And that's kind of like the easy part. So that's what we're going to do first. So if I look at this number, I've got my, I call it the stem. I don't know what it's really called. You could ask Miss Safer if she's there today. So I look at this number, and first I just see that, okay, it's 2 point. So it's like one digit point something. So that number, 2.0075, falls within this category between 1 and 10, but not up to 10. My power of 10 is 6, so what this 6 tells me is that all I need to do is move my decimal point 6 times to the right. So I would do that by going 1, 2, 3, 4, 5, 6. And so I've got these 2 extra empty spaces, and so I fill those with zeros. So I'm going to come over here, and I'm going to write that. So 2007500. And again, these 2 extra zeros are coming from moving my decimal point 6 times, and I had these 2 empty spots to fill. Now I can go back and add in my commas. And so what this means was that in scientific notation, 2.0075 times 10 to the 6th is really the number 2,007,500. On the next one, because my power of 10 is negative, it's telling me to move my decimal point to the left. So I would go 1, 2, 3, 4, and now I've got my decimal, and this time I've got 3 empty spaces to fill. So this would be 0.000 from those 3 empty spots, 1685. And then if I wanted to really name this number, I'd have to count out my place value. So tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions, 10 millionths. So this is 1,685 10 millionths. Or I could write it in scientific notation. So there's 3 more here. I want you to try these on your own. You're going to look at your power of 10 and decide which direction you're moving your decimal point and how many spaces you're moving it. And your final answer in standard notation will go on this line. Pause the video, press play when you're ready to check your answers. So on example 3, my power of 10 was +5, so that was asking me to move my decimal 5 spaces to the right, which left me with 1 extra space to fill with my 0. So that's the number 702,350. On both examples 4 and 5, my power of 10 was negative, so I'm moving my decimal point to the left. On this one, I moved it to the left 7 times, which gave me 6 empty spots to fill with these zeros. So I've got 0.000003096. And then on example 5, I went 4 spaces to the left, which gave me 3 empty spots to fill with these zeros, so 0.00045. So going from scientific notation to standard notation is pretty simple because all you have to do is look at the exponent, decide which direction you're moving based on if it's positive or negative, and move that many times. Going from standard notation to scientific, sometimes people find confusing, but we'll try to do the best job that we can here. So the first thing that I have to do is I have to find my C value, or that like stem number that's going to be multiplied by the power of 10. And this is where I have to remember that it has to be between 1 and 10, and it can equal 1, but it cannot equal 10. And so what that means is I want 1 digit before the decimal, and as many digits as I need after the fact is fine. So right now in this number, 42,590,000, I don't see a decimal point, but it's here. It's at the end of the number. So the first thing I'm going to do is put that decimal point somewhere in this number, so that way there's only 1 digit before the decimal point. So I'm going to move it over here, and so I'm going to put it between the 4 and the 2. So now it's going to be 4.259. And the idea of scientific notation is it lets me write less because now I don't have to write these zeros. So 4.259. Now I want to look at this and decide what would I want my reader to do if they were looking at this C value in order to get back to the number 42,590,000. Would I want them to move the decimal point to the left, or making the number really, really small? Or would I want them to move the decimal point to the right, making the number really, really big? I would want them to move it to the right. So what that means about my power of 10 is that my power of 10 is going to be positive. Now I just have to figure out how many times would I want them to move it. And so if I go back over here where I put my decimal point in between, I would just count out how many times it would take me to get back to where the decimal originally was. And so I would go 1, 2, 3, 4, 5, 6, 7. So that means my power of 10 is positive 7. And so now if someone took this answer and converted it from scientific notation back into standard notation, they would look at this number 7, say it's positive 7, they would move it 7 times to the right, and they would end up with 42,590,000. So on my next one, the first thing I want to do is figure out where I need this decimal to go, so that way I've got a C value between 1 and 10, at least 1, not up to 10, and so I've got 1 digit before that decimal point. So that spot is going to be between the 5 and the 7. And so instead of writing all of that long number, I can just write it as 5.74. And that C number is between the 1 and the 10. The next thing I want to decide is if my reader was looking at this C value, where would I want them to move this decimal in order to get back to this really small number? Would I want them to go to the left, or would I want them to go to the right? Since it's a really small number, I want them to move to the left. What that tells me about my power of 10 is my power of 10 is going to be negative. Now I just have to figure out how many times do I want them to move it. So I would start here and count backwards. 1, 2, 3, 4, 5. So that means in scientific notation, my final answer is 5.74 times 10 to the negative 5th. And if someone tried to convert this, they would start at my decimal point and they would move back 5 times, arriving at this standard notation number. Okay, so for examples 8, 9, and 10, I want you to try putting these in scientific notation. Make sure when you put the decimal point that there's only 1 digit before the decimal point, and then make sure when you have your exponent that it's telling the reader which direction to move in order to get back to the number that we started with. So you should have, we just set this one up with like times 10 to the, and then an empty block, but each of your answers should look the same. So this one would be something times 10, and then make sure you have an empty space there. So pause the video, press play when you're ready to check your answers. So on example 8, I would begin by putting my decimal point between the 5 and the 3, and then I would want my reader to move that to the right in order to make it into a big number, so it's a positive power of 10, and I would need them to move 5 times. So 5.39 times 10 to the 5th. On example 9, I would start by putting my decimal point between the 2 and the 6. So I've got 2.675, and then if my reader starts here, I would want them to go to the right, so it's positive, and I need them to go to the right 8 times to get back to the 267,500,000. On example 10, my decimal goes between the 4 and the 8. I want my reader to go to the left, so my power of 10 is negative, and I want them to move 4 times to the left. So 4.86 times 10 to the negative 4th. The next thing that we can do with scientific notation is order the numbers. We're going to do it by keeping them in scientific notation. It can be a more efficient method. Some people might change them all to standard notation, which is totally fine, but for right now we're going to do it by doing scientific notation. So first I would change my 103,400,000 to scientific notation by doing 1.034 times 10 to the 8th. So my decimal goes between the 1 and the 0, and I would need to move 8 times to get back to scientific note to get back to the 103,400,000. My next one is I would make it 8.076 times 10 to the 7th. So right away, of my 3 answers, I can see that this one is the smallest because it has the lowest power of 10. So that means that my 80,760,000 is my least number. I just put it there by accident. So I would put that over here. 80,760,000. And I'm writing, even though I changed it to scientific notation in order to compare them easily, I'm writing it in the form or the notation that it was given to me. And this number was given to me in standard notation. So next, I've got these two numbers that both have 10 to the 8th power. So the next thing I'll look at is their C values. This C value is 7.8. This C value is 1.034. So that means that 7.8 is going to be bigger. So my next number is going to be 103,400,000. And then my final greatest number is going to be 7.8 times 10 to the 8th. So let's do one more of these, and then we'll move on to multiplying and dividing. So I've got 93 million is 9.3 times 10 to the 7th. Then I have the next 9.2 times 10 to the 6th. And finally, I'm going to have 9.028 times 10 to the 6th. So now I would look at my powers of 10. So I've got 10 to the 7th, 10 to the 6th, and 10 to the 6th. This is going to be my biggest number. It's the highest power of 10. So on this line at the end, because I'm going least to greatest, I can write 93 million. Then, since my next two have the same power of 6, I would compare their stem numbers, or their C numbers. 9.028 compared to 9.2. This one is smaller. So my next number is going to be 9,028,000. And then my middle number I'm going to write in the notation that was given to me, which was scientific notation. So here are my 3 numbers in order from least to greatest. So the last thing that we can do with scientific notation is we can multiply or divide in scientific notation. And I'll show you why this is actually a more efficient method than doing it in standard notation. Most likely, if you encounter problems like this on the MCAS, they're going to be on the non-calculator section. So don't write this down to start, but I just want to show you this inefficient way. So I'll even say, don't write. And I'm not even going to do the whole thing out. So one thing you might think is, okay, let me just change this to a standard notation number by moving the decimal 2 spaces to the right. So that would give me 850. And then times, if I change this to standard notation, I would move it 6 spaces to the right. So that would be 850 times 17, and then I would have to add my 5 extra zeros. So I'd have to do out 850 times 1,700,000. And so imagine doing that without a calculator. You certainly could, but you would have to set it up like this. And you'd have to do out long multiplication. And so that's probably going to be a really inefficient way to do it. Instead, what we can do is we can do the scientific notation method. So I have 8.5 being multiplied by the power of 10, 10 to the second. I have 1.7 being multiplied by 10 to the sixth. And remember that these back-to-back parentheses indicate or imply that you're multiplying. So really in this entire problem, I have 4 items that are all multiplying each other. And with multiplication, one of the things that I can do is I can change the order that I multiply. So I could multiply 8.5 times 1.7, and I could also multiply 10 to the second times 10 to the sixth. Well, this we did very recently. We learned that if we're multiplying and the bases are the same, if you think about like x to the second times x to the sixth, we learned that that shortcut was that we could add those exponents. So x to the second times x to the sixth would be x to the eighth. Similarly, 10 to the second times 10 to the sixth is going to be 10 to the eighth. So now all I need to do is multiply my two c values, 8.5 and 1.7, which is still annoying without a calculator, but a much simpler problem to do rather than that big with all of those zeros. So I've got 7 times 5 is 35. I'm going to carry the 3. 7 times 8 is 56, plus 3 is 59. Add my 0. 1 times 5 is 5. 1 times 8 is 8. Now I add 1 to carry 13, 14 again. So I ended up with 14 and 2 decimals, 14.45 times 10 to the 8th. So you might be thinking, hey, that's great, we're done. Well, there's one problem. Remember that this number was supposed to be between 1 and 10, but couldn't go over 10, or it couldn't be 10 or over. So 14.45 is actually not the right c value. So I'd have to say, hey, decimal, wait 1 second. I need to bring you back 1 space. So what's going to happen to this exponent when I bring it back 1 space? Well, right now, if this was fine, if I was allowed to keep it like this exponent would tell me to move my decimal 8 spaces to the right. But by bringing it back 1 space, it's getting 1 space farther away from its final destination. So this becomes 1.445 times 10 to the 9th. So again, the reason that happened was, think of like if someone was cheating in a race by taking a 1-step head start, right? And the finish line was 8 steps away. So here, this decimal is only 8 steps away from the finish line, but they're cheating. They're actually supposed to be starting here. So when we grab them and pull them back, they're now where they're supposed to be, which is 9 steps away from the finish line. So one thing that's important is to adjust your answer if needed to make sure that it's accurately in scientific notation. Okay, let's look at example 14. So I could change this to 0.0012 and then square that, but that would be annoying. Or I could apply my exponent property, which said that if a is multiplying b, which 1.2 is multiplying 10 to the negative third, and they're getting exponented, or any exponent, both a and b can receive that exponent. Oh my goodness, that was an F. And so this exponent of squared is touching the parentheses, which means both items inside the parentheses, 1.2 and 10 to the negative 3, are receiving the exponent of 2. So what that means for me is I'm doing 1.2 squared times 10 to the negative third squared. Remember, if I do a power to a power, my shortcut says I can multiply. So that's going to become 10 to the negative sixth. Then the only real math I have to do is 1.2 times 1.2. Well, I know that 12 times 12 is 144. And then it would have 2 decimal places. So this will come out to 1.44 times 10 to the negative sixth. And the nice thing is the decimal is in the correct spot. I don't have to make any adjustments. So we're good to go there. Let's look at a division one. So I'm going to try example 19. So again, I could make this, change it by move it 4 spaces to the right. And so then I would have 1, 2, 0, 0, 0 divided by 0.0016. But without a calculator, that's going to be a real pain to accomplish. So rather than do that, I'm going to do my rules of exponents, and I'm going to divide these two, and I'm also going to divide these two. So this is kind of like doing what we saw this past week, which was like 2x to the third over 4x to the seventh or something like that. I treat the 2/4 as its own problem, and I treat the x's as its own problem. So here I'm going to divide 1.2 by 1.6, and I'm going to divide 10 to the 4th divided by 10 to the negative third. So because these have the same base and they're being subtracted, I'll actually change these to make them match. They're dividing, which means, sorry, I think I said they were being subtracted. They're being divided, which allows me to subtract. I could do 4 minus negative 3, or I could actually bump these 10s up, because remember, that's how exponents negative exponents operate. Whether you bump the 10 to the negative 3 up and make it 10 to the third, or you do 4 minus negative 3, in the end, you're going to end up with 10 to the 7th. And so now I've still got to do my 1.2 divided by 1.6. And you might be thinking, well, that's still not easy to do without a calculator because it's a decimal. What I would do is I would move that over, make it 12, and then golden rule, whatever you do to the top, you do to the bottom, 16. Then I would reduce 12/16 because they're both divisible by 4, and that would get me 3/4. Now, with scientific notation, we don't write a fraction, but I know the decimal equivalent of 3/4 is 0.75. So I've got 0.75 times 10 to the 7th, which looks great. Here's my decimal, and my exponent is telling me to move it 7 spaces to the right. But we have that problem again in that this number is supposed to be between 1 and 10. And 0.75 is just too small. So right now, the decimal is 7 spaces away from where it's supposed to be for standard notation if I were to convert it, but it's really supposed to be starting between the 7 and the 5. So this should say 7.5 times 10 to the, now what I just did is when it was here between the 0 and the 7, it was 7 spaces away from its ending spot. I moved it 1 space closer, and so now what that means is it's 6 spaces away. So my answer in scientific notation is 7.5 times 10 to the 6th. And again, here, my exponent was telling me to move my decimal 7 spaces to the right, but it's like, hey, wait, you're not really at the starting line yet. The starting line's right here. So we move it to the starting line, and when we did that, it got 1 step closer to the finish line, which is now only 6 spaces away. Okay, so these are a little bit more complicated, but I do want you to give them a try, and then you can definitely come back and look at the video when you're ready to check your answers. Now for today, what you also can do is when you're doing like this kind of multiplication or this kind of division down here, feel free to use a calculator for that, even though on MCAS you won't have one. But I do want to make sure you're doing it in scientific notation. So making sure that like on this one, you're going to start by multiplying 5.7 times 2.6. That you could do on your calculator, and then do 10 to the third times 10 to the fourth. So don't convert them to standard, but feel free to use a calculator to make this part a little bit more efficient. Just know that on MCAS or something like that, you would actually be asked to do it out by hand like this. And then the last thing to make sure of before you check your answers is that your C value is between 1 and 10. So you might have to make an adjustment, which is going to affect your exponent, depending, and you want to think, is it getting closer to the finish line or farther away? So it's either going to make your exponent larger or smaller. All right, so you're going to try examples 15, 16, 17, 18, and 20 and 21. Pause the video, press play when you're ready to check your answers. Okay, so on example 15, you do 5.7 times 2.6, and you get 14.82. 10 to the third times 10 to the fourth is 10 to the 7th. So it looks like the answer should be 14.82 times 10 to the 7th. Right now, my decimal is here between the 4 and the 8, and it's 7 steps away from the finish line. But wait, it's not at the starting line. The starting line is here. Back up 1 step. So when we back up the decimal point by 1 step, it's now 8 spaces away from the finish line. So in scientific notation, it's 1.482 times 10 to the 8th. It's important to know that these will both get you the same answer for standard notation, but that when scientific notation was created, they made this decision that this number just had to be between 1 and 10. So this isn't officially in scientific notation. On example 16, we start by squaring 2.4 because this exponent of 2 is being applied to both items inside. 2.4 times 2.4 was 5.76. And then 10 to the negative fourth to the second, I get to multiply my exponents and get 10 to the negative 8th. And the nice thing on this one is there was no adjustment to be made. On example 17, my exponent is being applied to 1.3 and 10 to the negative 5th. 1.3 times 1.3 was 1.69, and 10 to the negative 5th to the second is 10 to the negative 10th. So 1.69 times 10 to the negative 10th. On example 18, I do 1.1 times 4.2, which came out to 4.62, and then 10 to the 7th times 10 to the second was 10 to the 9th, and no adjustment was necessary. On number 20, I start by dividing 4.5 by 1.5, which came out to 3. Some people just say 3, or you can say 3.0. It looks a little more normal because scientific notation usually has that decimal point. Then 10 to the 5th divided by 10 to the negative 2nd. I could do 5 minus negative 2, or I could bump up my 10s to the top, making it 10 to the 2nd. Either way, in the end, I have 10 to the 7th. And then on 21, I started by dividing 2.4 by 2.5, and that got me 0.96, and then 10 to the 5th divided by 10 to the negative 4th was 10 to the 9th. The problem here is, here's my decimal, it's 9 spaces away from the finish line, but it's not at the starting line yet. It has to step one step closer to be at the starting line, and when it takes that step, my exponent becomes 8, because if it's 9 spaces away from the finish line here, and I move it one step closer, now it's only 8 steps away.